maybe we using that in future. So you need to press the allow that's in the bottom. Otherwise, Zoom won't allow you to continue. Okay, so I recording this in case that so after this presentation, you may need to reference the recording for your later of the revision of the modeling. Okay, so I share my computing screen again. Okay, so we have that in the software, so which looks like so this. Okay, I firstly that's in the close this in the software. Yeah, then I open that in the GUI version of our software. Okay, if you open that in the version, that's in the software, which looks like so this. Like that, I wanted to do that in the BTS test. So you can okay, I have that in the border. I have already done that. I just open that. Yeah, so this is that in the two-dimensional model. I needed to choose that in the view. So I needed to choose, make this becomes bigger. Okay, I show that in the firstly of that in the step. I'm making this on view. Okay, for you to do that in the modeling, you firstly need to have that in the base. Yeah, so for our case, we do not generate the base of ourselves. We were using that in the third part of the program, like that in using the abacus. Okay, so then that's important that you know that in the third part of the program. Okay, so for example, we using a free version of that in the abacus. Yeah, using the abacus is easy for you to generate this kind of meshes. Yeah, so is that necessary for me to demonstrate that how to use the abacus in the other way, or I can skip this? Yeah, you can look in that in the tutorial which is available on Malo. So how not on Malo, so that's on that in the website, which is showed you how to use that in the abacus to generate this kind of meshes. Yeah, okay, I was skipping that since this that's actually which is too simple. Okay, for the abacus, after using the abacus to generate the meshes, okay, you can output in this mesh. Okay, you can go into the job. So then you create a job. Okay, so that's in the job. So then you will go into, okay, you create a job like here. I have that in the BTS2D. So then I create you can give that in any of that descriptions there. Okay, then you have the job. If you click on this one, so write the input. So from the abacus, actually you will get an input file, the file which looks like this. Okay, so let me find that in the file. Okay, this is that the measure of the information of that in the BTS. Okay, you generate the geometry. So in the abacus. So then after that, you divided that into the meshes. Then you can write an output. So then the output is a data file. Okay, so this data file is what we are wanting. So let's look in this data file. Okay, this data file is like that. You have 3 of the parts. Okay, that's easy to understand. Okay, we have that in the Brazilian test. So if we simply need to draw that, is like this. So we have that the top plate, so which is correspond to this one. So then you have that in a bottom plate. Okay, so here, so this is the bottom plate, okay, which is correspond to this one. So then you have a rock sample that's in the middle of that here. Okay, so this, which is corresponding this one. Okay, for each part and each of that, you will have that the, okay, we say here we have that the element. Like in here, this is one element. Okay, each of the element, you will have an element number. So for example, I have this element number 1. So then you will have that the node as well. Okay, so the node, yeah, suppose I have this node 1, then that's node 2, so then that's node 3. Okay, so for your case, you can see what is that obstacles which will automatically to generate this for you. Firstly, looking at for the first of that the parts log. Let's look at that in the data. You have that in the nodes. Yeah, the nodes. The first one, which is the node number. Okay, so if I draw this, yeah, the node number, you have that in the firstly node, which is correspond. This that's the node number, and that is so on 1, 2, 3. Then you have the coordinate. Each of the node, you will have an x coordinate. So you will have a y of that in the coordinate. So then what is this? So here, this is the x coordinate. So then that's the y coordinate. Yeah, then for all of the others, so that's the same of the pattern. Okay, let's go down. So you will have that in the node. So then you will have that element. So element, you have the different type. So like in yours, so we are do the 2-dimensional modeling. So here, this is that's the plane strain, or that's in the plane of the stress of the triangle of the element. So we know that's in the triangle element. So you only have that in the 3, each of the element have 3 nodes. Okay, so that's for the first element, the element 1, then I have that in the node number. That's equal to this node number, which is 205. Okay, so then this node number, which is 206. And then this number, which is 207. So this is what is the first row is me. So the first one, so this is the element number. 205, then that's the first node, then 206, second node, and the 207. So that's the third of the node. So all of that in the data, the remaining of the data, which is follow the same of this kind. You can see the second element. So then the third element and so on, till that's the loss of the element. Okay, so that's represented for the a rock sample. Then for the plate, the top loading plate, or that's the bottom of the loading plate. So you have this is a sphere, that's the node. So then that's the element number. And for the bottom of the plate, you can see, so that's a sphere, that's the node, and that's the bottom of that animal. Okay, so this is that's the base of the information which we are needed for our modeling. Okay, let's come back into the pump handle presentation. Yeah, so for our to do the modeling for the base, so which is from that kind of a software. Okay, for us to use that in the mesh, we use that in the mesh from the abacus. Okay, let's look at this. Yeah, we put in that in the beginning test. We have part 1. Okay, we have that's the rock. So then part 2. So that's the top plate. So then part 3, that's the bottom plate. Okay, so firstly, let's look at that in first of the parts. Okay, so first part, that's the rock. Yeah, well, before we given this, we needed to give some of the general information. Okay, so here we have that in the general of that in the information. You notice that we firstly need two number. We have these two number. Okay, we have 5,378 and 2819. So this is the total number of the nodes and the total number of the elements. Okay, so you have the rock. So you have that in the element number, another number 1, 2, and so on. Like that, we have here for the rock. So we have the element in the number, which will have 5,294. Then we have the node number, which is 2,735. Okay, so then we for the plate, top and plate, bottom plate, so you will have the element number and the node number. So we added them together. Okay, this is that's the total of that's the element number, and then 2819. So which is the total of the three parts we adding together, which is equal to this one. So that's what it means. Okay, we have three parts. Yeah, then and at the top here we have the total number of the element. So then here that's the total number of the nodes. So then inside of each of the parts, so like this is the part of the rock. Okay, we have that. What is the number of that? The okay, before I go back, these two number, which is the total number of elements inside of this part, total number of the nodes, so inside of this part. Yeah, then we follow that in the abacus, the notation. We have here, we given that in some of the cases, you may need to move this. Yeah, so for example, if I, in the abacus, if I building that in the top plate, I building that in the location, actually is here. So then in that case, it's unnecessary for me to rebuild that. I just remove this. Okay, I given that in, suppose that I have that, and this is that in the y direction. Then this is that in the x direction. Okay, I just needed to move that in the plate, okay, to this location. Okay, suppose that I have this location, so y is equal to, so y equal to +1. And then initially what I built in this actually y equal to 0. So then I just needed to put in that and moving that in upward, moving one of that in the unit. So then I have the plate which will be here. Okay, so for your case, most of the cases you do not need to use that. You just so keeping that as 0. Okay, so then for the element, what we just copy, that's the data from that's the abacus, then to that in our input file. Okay, so our input file, so that's where it looks like this, like that for the 2-dimensional of the predictions test. Okay, so let me look at that in the input parameter. I have already prepared this input parameter, so that's here. So we have that in the input parameter, which is like this. Okay, we can compile this with that in the abacus. Okay, so let me move in this. Okay, so let's look into that in the abacus. Okay, so this is that I already explained it. So then we have that the element. So actually, which is directly to copy what is generated Yeah, so we copy. So that's the element of that in the information, and so on. So then you put in that on that's in the element. Okay, we define here as a different type of the element. So here we using that in the 2-dimensional. So we using the triangle element. We define that the element type, which is 1. Okay, for your case, you can firstly ignore this part. Later, for example, when we do the 3-dimensional modeling, we needed to use the different element type. Then we needed to change this one. Otherwise, it's unnecessary for you to change this. Okay, then you look at that in this data file, we have this input file, so which is exactly the same as that in the output. So then here, this is the notes. So note, so what we do, we just copy, okay, like that. So I copy this part of that in the data. So then I paste that in here. So that's the node of that in the information. Okay, so this is that what we have that in the first part. Then after that, so we will have the second part. So like that in the top plate. So the top plate, which is the same. So we just copy that's in the data, which is from Abacus. Okay, so that's here. Yeah, so we have this, that's in the top plate. Then you have the note and the element. Okay, I firstly needed to know how many of the notes and element are there. For example, here I have that in, yeah, I only have 118 of the notes. I firstly to put in that the total number of the notes here. Then the total number of the elements. Okay, so for the top plate, I only using 154. Yeah, of that in there. So then I have that in the top of that in the nodes. Top plate is that's the element, sorry. So number of the elements, number of the nodes. Okay, so then here, so you notice that we have here moving this one. Okay, so this is actually which is the same as that in the upcut we didn't move that. So this is that we using that reducing the computation of the time, since what we will have that only when you have the top plate and the bottom plate, when you have the interact, so which will have that failure. So if you have that not interact with each other, so you have that calculation, which is the wastage of the calculation's cost. So what we is to move this is making sure initially the top plate, which is contact with that's in the rock of the sample. Okay, so here this is the same. We just copy that's in the elementary information, and that's in the copy of the node of the information. Okay, this is that's in the top plate. Then the third one, which is the bottom plate. So the bottom plate, yeah, actually, so this is symmetric is the same. So is the same as that's in the top of the plate. So you have that in the number of the elements, number of the nodes. Okay, so then that's the element of the information, and that's the node of that information. Okay, so with this kind of information, then we can, okay, so let me close this one. Yeah, so for this input file, I already prepared this input file, so which is on here. Okay, I open this. So then I say here, I will do a new modeling. Okay, I do a new modeling. I say, so I do a new modeling. So that's the test one. Give our name. So then you save, which will open the graph interface. So now we prepared this input file. So that we using our software to read this input file. Okay, then what you do is that from here, goes into here, that's the input. Okay, you click in input. So click on that and read the element and note information. Okay, you click on that one, so which will open a dialog. So the dialog is like this. Okay, so the dialog will ask you a few of the questions. So here is asking you whether we do that in the two-dimensional modeling or do the three-dimensional modeling. Okay, so now we are doing the two-dimensional modeling. So then you click on this one. So click on that in the 2D of the project. Yes, so here we have this software, so which is quite comprehensive. Many of that in the information, like in this part, for you to do that in the simple of that in the BTS test. So you do not need this part. Okay, so we ignore this part at this moment. So later, when we do the complicated test, like that, when we influence the fruit, when we put in that in the stress wave propagation, when we consider that in deep underground, you will have the in situ of the stress, how to apply the in situ stress. Yeah, so when we were using that in called that eccentricity of that zone model. Yeah, then you need to, when we need to consider that in the excavation, or we need to install the supporting systems there. So then, okay, at this moment, since we do that in the simple of that in the pre-resilience test, you can ignore all of this part. Okay, so you only needed to here, you only needed to say you will do that in the two-dimensional modeling. You chosen that in two-dimensional modeling. So then you click OK. So clicking OK, then our software will directly to read that in the input file which you prepared. That's using the outcomes. Okay, so let's click on that and say OK. You clicking OK, it seems, yeah, it tells you that's an element and a node topology file. So is reading correct successfully. Yeah, you click on OK, you see nothing. That's because we have that in the sample, which is quite small. Okay, you needed to zoom that. Okay, we have the defaultly show that is a three-dimensional model. We needed to change this view to the two-dimensional. Okay, you click on that, and okay, we show that in the XY plane, XY front view. Okay, you click on this one, the front view. And the default one, which will show the isotropic of that view. So you need to click on this one, which will show that called the orthographic of that view. Okay, if you click on this one, you will see that's a little bit, that's here is quite small. Okay, you can zoom this. Yeah, you click into this one. Okay, you zoom that. Yeah, so now you will see that in the bottom there. Okay, so the default one actually, so that's a field using that in the elastic modulus of that material. Okay, you can back in this becomes on field. You click on that and tools, click on this. Okay, draw the on field and that's model. Okay, so then from here, so you will see that's in the element and that's in the loading of that information. Here, that's quite convenient. You can zoom, further zoom up. Yeah, so you can see that's in the clear of the base. You can further zoom out. So see that's in the full of that in the picture. Okay, so this is that in the to prepare that in the base of that in the data. So after you have that in the mesh, we need to apply that in the boundary condition. We need to apply that in the load there. Okay, the boundary condition for this one, what we wanted to do is that actually, so for the plate, it's unnecessary for us to apply any of the boundary of the condition. But for the top loading plate, we wanted to move this top loading plate down. And then the bottom plate, you can fix the bottom plate, or you put in that in the bottom plate, which is moving up that one as well. So that which is through to given the boundary condition. Okay, besides the boundary, you need to given that in the material of the property. To given that in the material property, okay, you need to define this. Okay, so given the material property, so I needed to define. Okay, so for all of the elements, I given a label. Okay, so for like that's in the rock, I given that in a label. I give that a label. That's 0. Okay, then for the element of the plate, okay, I given a label. So that's 1. Okay, so this is that for the element. So then for the nodes, we needed to give that in the boundary condition, use that, right? Okay, for the nodes, if that I do not need to add anything, I given that in the node. Yeah, okay, I think that's it's better for me to use a visualization. Okay, so let me show that's in a visualization. Okay, I goes into that in the first day of that in the step. Yeah, I mentioned that, which is exactly the same as that what we just showed. Okay, so now what I wanted to use given the material property and given the boundary condition. Okay, given the material property, so what I given that here. So I making that in the rock, so I making that equal to 0 of that in the element which is given a label equal to 0. Then the top plate I given that 1. Then the bottom plate which is given that the 2. Okay, so this is that what is in that in the input file. Okay, so let's come back into this input file. So you look at that and further down of that in the input file. So we have a few of the model. So this model, I will give you a very simple of the C++ program. So this you using the C++ program, which I will give that to you. It's so easy for you to prepare this using that in the script. Okay, so firstly, let's look at that in an overview, how this is the structure looks like. Okay, firstly, that's the initial of the velocity. For our case, we have this model initially. We do not have any of the initial movement. So I have this that's everywhere. I given that in 0. Although we have the loading plate, so we were given that an movement, but this movement, so is I was given that through the boundary condition instead of that in the initial of that in the velocity. But there is a case, for example, we wanted to put in the flat of a rock, then the rock have an initial velocity, then in that case, you can given that into here. Okay, anyway, so here we have this initial velocity that's given to each of the nodes. All of that is 0. So have that in which is from the first nodes till that's in the last nodes. Yeah, but here you need to be careful. We have 3 of the parts. Okay, we have that in the top plate, we have that in the bottom plate, and we have the rock. Of course, for each of the plate, for each of the parts, So you have the element number and the another number which is separate labeled. For example, here you have that. For example, that's the 1 to 10. Okay, I say 1 to 1 to 100. And then for the top plate, so you say, so that's the 1 to 10. And here that's 1 to 10. But for our case, we have that, sorry, so this shouldn't, is 1 to 10. For our case, we have that in the sequential. Okay, I have here, this is that, okay, I use another of the color. I have here, that's the 1 to 100. Then here, I label that, that's the 101. So then to 110. Then here, that will be, so from 111, so here, that's 120. So that means that's the continuous of that in the numbering. Okay, so then given that in the element of that label, you can see initially that's the rock. All of that rock are given that 0. Yeah, everywhere. So if that's the element that belongs to rock, are given that 0. So if that's belongs to plate, you can see are given that the 1. So that's have that 0 and 1. Okay, so that's the element. So then let's look at that in the nodes. So the nodes, so are given that in the different. Okay, so I have that given that majority of that, I do not need to give anything. So I given that in 3. So then I have that given the 4. Top plate are given that in 4. Then the bottom plate are given that in the 5. Okay, then I have that in this one, which is called the, we know when we do this modeling, initially, you only have that's the contact which will happens that's here, and that happens here. In the order of the location, you won't really have the contact. Then in that case, so you ask the program, initially only needed to deal with the contact here. So then we tell the program, which is through given that's in the label, the majority of the location, so it's unnecessary for me to deal with that, or given that in 0. Otherwise, are given that in 1. You may say, okay, so this data file, which is terrible to prepare by hand. Yeah, it's true. If you prepare it by hand, so that's why terrible. But if you using Abacus and using a script, okay, so here, this is I prepared a simple of the script, well, very simple, just have one file of a program. So I coded that in the preprocessor, HFDEM preprocessor. Okay, so let me, so first we close this one to see, I close this one. So you see this program, I coded that in the script of the program. Okay, so let me show you this script. I will give you this script. So after we, this presentation, so I have that in, so it should be, yeah, so that's here. So you can see here, this only have one file. Only have one of that in the CPP of that in the file. If I open that using the TXT file, so that's like this. Okay, I open this using the Visual Studio. So that's why I say you need to install that in the Visual Studio. Okay, so let me, this script, actually can prepare that for any of that HFDEM of the modeling. It's not only designed that for a resilience test. I can use that to do any of that HFDEM test. You notice that you will notice that later when we introduce to do the 3-dimensional resilience test, and later to do more complicated of the test, we were using this scripting as well. Okay, let's quickly to look at that. Yeah, so for you to use, you need to have that really understand this program. You need to make that the small of the changes for each of the different of the problem. Okay, you can see this is that the typical of the C of the structure. So you have a main of the function. All of that is the information, which is the inside of that the main of the function. So what I defined a few of the temporary of the parameter. Okay, so here a few of the parts I need you pay attention. So the first one, which is the problem dimension. If you do the 3-dimensional modeling, you put in that equal to 1. If you do the 2-dimensional modeling, you put in that equal to 0. Okay, so here, the total number of the elements. So this is that in the data file, which we are prepare that in here. So you look at that in here. Okay, so the total number of that in the elements, yeah, which is this one. So you copy this data, which is pasted in that in here. So total number of the elements. Okay, so then here, so this is that's the total number of that in the nodes. Okay, after you give that one, so you can see here I given that I define a few of that's the temporary of that parameter. You can ignore that. So I will read a file. Okay, so then here is, let's firstly, we just said in this model. So I have that in the element, the rock, I will give that 0, and then plate, I will give that 1. How I do that? I just needed to use one sentence. So in that this script I can implement. You can see, so I do a loop, which is starting from the first element till that's the last element. Okay, so here you need to pay a little bit of attention. So in that you can see for the array, so you starting from 0, but in the obstacles, so you have that number always starting from 1. Okay, I have from loop from the first element to the last element. Since I know that's in the for rock, I have that an element that's in the, okay, so let me come this one. Yeah, so for the rock, I know of that in the elementary number which was smaller than this. You can see if I have this smaller than this, so then I given that 0. So I indicated that's a rock. Otherwise, I given that 1. So you can see it's very easy. You just use one sentence. So then you can specify of that in the elementary rock, you given that 0. And then for the plate, so you given that 1. Okay. So that's for given that in the element. Okay, so then after that, you given that in the nodes. Okay, so in the nodes, we say for this one, we have the rock. If that's the rock of the nodes, we were given that in 3. The top plate we give 4. Then the bottom plate we given that in 5. Okay, so it's easy for you to implement that in one as well. Okay, it goes into this. Okay, you can see here. I know that's for the rock. I have that the node number about to be smaller than this one. So then I give it, if smaller than this one, so that's the rock's node. So then I give that 3. If bigger than that one, I give that 4. Yeah, obviously we said that we say we have the top plate we given 4, but for the bottom plate, actually I wanted it to give that a 5. But at first it given that 4. Then after that, I will overwrite that. I read in that the, okay, so I will read that the a note of that in the bottom plate. So in our course, it's very easy for you to define that kind of a set. Okay, for example, I wanted to define, I wanted to know any of that in the particular of that in the error. Okay, so you can define that in the sets here. Okay, so let me show you so that kind of a set. Okay, I already defined this the sets here. Yeah, so the set. Yeah, okay. Sorry for this one. So I didn't define that in the sets. So let me open another one. Yeah, so I already defined the sets there. Okay, so I should have already defined that in the sets here. Yeah, okay, sorry for this one. I do not have that in the sets. Let me access a lot of the computer. So you will see. Okay, so I have that sensor here. Okay, let me show all of them. Yeah, so this is that's in the border which we are using. So I have already defined that in the sets. So inside of this, yeah, you can see here for the bottom plate. Yeah, I highlighted this one. So then you will see that. And I have that. It's very convenient for you to define any of that in the sets in of course using the graphic of that in the interface. Okay, so the sets. So after you define that, which will be that's the information, which is like this. Yeah, you have that in the set, like that in the bottom of the plate. Yeah, actually, which is from 1 yeah, to 118. Okay, so this is that. Okay, so then I can specify that's the node of that property. Okay, so then that's all. Then the remaining, I need to give an initial of the contact. Yeah, so that's green part is unnecessary for you to care for that. Okay, firstly, I given all of that nodes, I given that 0. Then for the part which I needed to have initial of the contact, so which is that here. So I define that in the set here. So okay, the rock I have initial contact. I only need to pick this notations there, then I given their label that's equal to that's the 1. And then the others, then the top plate and the bottom plate, so I given that's the 1 as well. Okay, so then that's solving that. And so what is that here? 0 and 1. Okay, so then you run this one. So then if we run this one, then which will automatically to generate this part. Okay, so I set in a few of the breaking point. You can use that breaking point to choose the program will run correctly or wrong. Okay, so after you run that, which will generate, yeah, you can see, so this is that what I want. So then here, that's where generation, that's the velocity. So generation, that's the animal property. So learning property. Yeah, then boundary property. Okay, then you copy this. You copy all of that. Okay, so then you put in that into the data file, which we are preparing. So which is this one. Okay, you can see this is exactly the same of that. So suppose we have this one, then you need to copy that one, then you paste that into here. So that's where automatically, which will prepare that in the data. Yeah, so for you, then you paste that. Okay, so we say we have that number. We given that 0, 1, 2, 3, 4, 5. What is that? The million. Okay, what are we given that in 0, 1? They are which is represented here. I have 9 columns of the data. Okay, I have this first column. I say that's 0. So then this is 1. So then that's 2, 3, and this is so on. Here I have the last column, so that's 9. Each column, which is represent either of the boundary condition or that's the input parameter. Okay, so let's look at that. What kind of input parameter we using the qualified model. Okay, so we were inputting what is the cohesion, and we can give a Weber distribution like the RFPA. So we can give a homogeneous index. So if you have that homogeneous index, which is quite big, so that means which will be a constant value. Otherwise, this will follow. That's the Weber distribution. Okay, needed to give that in the parameter, yes, for the friction angle, for the tension strength, and so on. Yeah, so that's the values of this kind of a parameter. Okay, I will focus on introducing 3 of the parameter. One of that, we in that we needed to give an elastic modulus and the Poisson's ratio. Yeah, actually, we are not directly to using the elastic modulus Poisson's ratio. Instead, we using lambda, and that's the U. Okay, we know that's lambda and the U, so that's a function of the elastic model. You can easily find that from the elastic book, like that the U, which is equal to elastic modulus divided by 2 multiple 1, and then that's the Poisson's ratio. I think that's lambda. So that's lambda constants. So which is equal to E multiple the Poisson's ratio. Yeah, and that's 1 added the Poisson's ratio. Then you will add 2 times of Poisson's ratio. So that's as long as you give that elastic modulus and that's the Poisson's ratio. So then you can calculate this the lambda and the U. Okay, this is one for that parameter. And then the other one is that we say inside of that, between of that the triangle element, we insert the cohesive element. So this cohesive element which will fail, then you are more than that, you are able to more than failure. Okay, this cohesive element, So then you need to give that the strength. Okay. For this cohesive element, we need to give that the cohesion. Okay, so that's that. So I given that the cohesion, which is 5 megapascal. I given that the tension strength, which is 1.7. That's the mega of the pascal. Okay, then here you will have that the how control that the failure. We say we have the cohesive element. So we have the constitutional relationship which will liken to this. So after the fail, so you have that energy which is like this. So during the fail, you will have the energy release. So this is that which is so-called G1 energy release. So G1 and the G2. So you need to give these parameters, so that's in the L as well. Okay, so then the order of the parameter is unnecessary for you to touch on that. With our presentation progress, I will gradually introduce the order of the parameter. Okay, so then besides that, we were given the boundary condition. So the boundary condition, which is given that in here. Okay, all of that. So if that's 2, which means you given yourself weight. If it's 3, so we given that no displacement. So looking at that, so we have that in the top plate. Okay, this is that. We have the top plate. So we given a elective value since that's we have the axis y direction, which is pointed upward. So this is that's in the x direction. So that means we pushing that in upper plate down with 0.05 meters per second, and the bottoms so up, which is 0.05 meters per second. So after you prepare this, okay, so then the next step is that we have that in the complexity of that in the data here. So then we reach that. Okay, then you can specify a few of the control parameters, how you wanted to use this. You can modify this using that in the graphic interface here as well. So like that. So what is that in the time step? Okay, so for example, for this one, we will run this. Yeah, so here we have this that in the explicit of that in the finite element method. So explicit finite element method, you will have that in the time step, which is quite small. Okay, here for you to run that, so you have 2 ways to run that. One way is that in HPC version. So we have all of the control of the information. So we put in that into an input file, or if you using that in the graphic of the version, so then each of that, so you using the graphic interface. Okay, since for the demonstration purpose, it's better for me to demonstrate in that using the graphic of the version. Okay, so for example, we wanted to control here, that's the time step. Okay, so for example, for this one, we will specify of the time step. If that's the HPC version, you have that in the time step, which is specified here. Okay, we specify the time, which is 2 nanoseconds. Okay, then the order of the parameter you can ignore at this point. So we place that, okay. Okay, so then here you can, yeah, so already just in that in the element there as well. You can already just in that in the notes as well. Most of that is only after you prepare that in the file is unnecessary for you to change this from the graphene. You can define that and how they interact with each other as well. You can specify, so that's the material property. We already specified that from the input file. You can give that the material property. So what kind of a model you wanted to use? Yeah, we using the Mercury model. And this can do, we have this very comprehensive, we can do, like in the SHPB test, which I showed that to you before as well. Okay, so here is unnecessary for you to change anything. Okay, so then the next step is that what kind of output you wanted to do that. For example, here I wanted to, output that have the OpenGL of that the visualization. I wanted to get in the stress strain curve. Then press OK. Okay, so then making that in the field model. So then you tell that the program is wrong. Okay, so here we follow that in the HP. Okay, suppose that we wanted to run some these steps. Okay, that's the total number of the step. I have every 2,000 of the steps. Okay, I have every 2,000 steps. So output on a result. So here we already do the mechanical of the analysis. We can do that in the thermal coupling, the fluid and the structure coupling. Okay, so later we will introduce that later. Okay, if I click on OK, then the program which will automatically run. If you use that in the graphic version, so that will be that's a little bit that's slow. If you use that in the HPC version, so that will be much of the faster. So during the running, it will automatically update the visualizations that's here. So you will see that's like that, and this is the second step of that calculation, which we're given that the results as well. Okay, so this is that for the graphic version. Actually, so this version is not so efficient. The better way is to run that using the HPC of that version. Okay, HPC version, like that, suppose that we wanted to do that. Okay, so let me build in that a new of that in the folder. So I build in a folder here. So I build in a folder assay. That's DLUT. Okay, I only, if I use the HPC version, so I only have the input of the exe file. So then I have that's the input file. Input file just this one, and that's the running control. Okay, so after this presentation, I will give you this input file. Then you will be able to do this modeling. So that's on your side. Okay, so for this, that's in the GUI version. So let's stop since that one. Since let's stop since this. Okay, let's stop in that and demonstrate how to use that in the HPC version. Okay, using HPC version, so that's very convenient. So we entered to that folder. So you entered to that folder. Okay, so then you only need to input that in the exe file. Okay, then you press that in. Okay, it will automatically to read in that. Then you give it a lane. Okay, we say that BTS2D test. Okay, so then that will automatically run. Cannot open. Sorry, so that's not a BTS of that. I needed to copy that's in the BTS input file. Okay, so let me delete that of that. Okay, so let me copy this to that's an input file. So then here you need to always change it. Okay, the control parameter, which is called the running control parameters. And here, so for the base, it's always called element, not topology. Oh, sorry, for two-dimensional modeling, so which is 2D, and then the other for 3 dimensions, that's 3D. Okay, so let's run that. Yeah, so we say that's BTS. Yeah, you can see that's run very fast. For this two-dimensional Brazilian test, you only need about 10 minutes. So then that's where I completed the calculation. Okay, so after the calculation, what is that in the output? So the output you can use if you use the GUI version. So our software will directly to deal with the visualization. If you use an HPC version, so you can use a program called ParaView. ParaView, so that's an open source of the program. You can download that from the web free. Okay, so license that. Suppose that download a open view, a ParaView. Okay, so this is that calculated that BTS3 two-dimensional modeling. So open that, you click on that and apply. Okay, so here, for example, if we wanted to show that the stress, x direction of the stress, okay, you can see, then you can click and play. Okay, which will show you the flow of the process from that the loading, the stress concentration, then till that the failure occur. Okay, stress concentration. So then after that, you will see that's in the crack, which will appear. Damage, then the crack can appear. Yeah, then see that's in the crack can appear. Even the crack can appear, we can follow the load instance on that. You can see, I think that's in RFPA. So after you have the crack appear, you cannot follow the load instance of that. You cannot have that in the value wide of that in the opening of that in the crack. Okay, for the video, which I showed you before of that video, which is prepared that's using the ParaView. You need to spend some time to be familiar with the ParaView. And you can also to see what type of the damage is there. Different damage of the top. Okay, you show that the this is the all type of the damage. You can show that in the mixed board damage. So you can show that in the pure board 1 and that's in the pure board 2. Yeah, obviously we have very few pure board 2. Okay, so that's for the HPC version. If you're using that in the GUI version, yeah, so then everything you can do that in GUI version, like that. Okay, so suppose that for the model which we already finished, so that you bring back into that model. Okay, so then you have that in the making that becomes bigger. Yeah, you can click and see. Okay, this is the first step. Yeah, so then goes on step by step. Yeah, so then goes into the last step. You can show that in a particular of that in the step as well. Yeah, so if I wanted to show a particular step, yeah, for example, I wanted to show 100 of that in steps, how that look. Yeah, then during that in the loading, yeah, that's 100 of the steps. Okay, so that's the show that in the failure pattern. Okay, after your calculation, you will see there is an input a file. Okay, that file is that yeah, which will have that in the contact force of that in the input file. This input file is that including the force. You can open that in the file using Excel. So then you can to get in that in the completely of that in the stress strain curve. Yeah, okay, so yeah, I have this that in the every of the step which I introduced here, actually, which is in that in the compounded presentation. Although I didn't use that one, since I think that if I just using that in the compounded presentation, it will be difficult for you to understand. Yeah, but after I interactively introducing how to you prepare this and that in the data, it will be revisit this in the compounded presentation. Yes, so this is that in the procedure which I operated that interactive. Yeah, so all of these depths, yeah, I already prepared that in the compounded presentation. So you can follow this compounded presentation step by step to operate in that in the software, and then to show that in the part view. Okay, so here this is that using another of that model of that to show that in the part view of that in the results. And here instruct you how to use the part view to do that in the output. Okay, so that's all I wanted to talk. Yeah, so I already, yeah, a little bit that's in the overtime. Okay, so I'll stop that in here. I hope that after you listen this presentation and receiving the input file, then you will be able to use the software to running this model at your side, then to get all of the results. Then yourself will be able to model any type of the resilience test. Either have that in the stretch of the loading surface or that's in the curve of the loading surface as well. Okay, hand back to you, Jennifer.
Okay, Professor Liu. Thank you for your very detailed presentation again.
Yeah, you're welcome.
Yeah,
let me. Yeah, sorry. Let me stop